Dear students, in this class we will derive the second law of reflection from the Fermat's principle. That is, derivation of second law of reflection from Fermat's principle. So we are going to derive the second law of reflection from Fermat's principle. So before going for the derivation, first we should know what is the second law of reflection. As per the second law of reflection, it says that the angle of incidence is equals to the angle of reflection. That is, whenever a ray of light incident on a plane mirror, we know that it undergoes reflection. So when a light incident on a mirror, it undergoes reflection. So in that case, the angle of incidence is always going to be equal to that of the angle of reflection. That is, I is equals to R. That is the second law of reflection. So here we are going to prove it. We are going to prove that the angle of incidence is equals to the angle of reflection from the Fermat's principle. Right? So for that, we have a diagram here. If you look at this diagram, here M dash is a mirror. We have an incident ray AO, which falls on the mirror M dash at point O. At point O, it undergoes reflection. So OB is the reflected ray. What is this? This is the normal. You can take it as ON. ON is the normal. So we have an incident ray AO. We have a reflected ray OB. ON is the normal. Then we know that this is going to be the angle of incidence I. This is going to be the angle of reflection R. This is the normal. The angle between the incident ray and the normal is going to be the angle of incidence I, and the angle between the normal and the reflected ray is going to be R. So now we have to prove that this angle of incidence I is equals to the angle of reflection R. That is, I equals to R. Or in other words, angle of incidence is equals to angle of reflection. This we have to prove, right? So for that, what we are doing here is to draw a perpendicular from A to B. The length of this is taken as small a. Draw a perpendicular from B to Q. The length of this is taken as small b, right? Then the distance from P to Q is taken as small d. The distance from P to O is taken as x. So if this is the distance d, if this is distance x, then the distance OQ is going to be what? It's going to be d minus x. So from here to here it is d, this is x, so this is going to be d minus x, right? Then, so if this is angle I, then this angle, alternate angles, this also is going to be angle I. If this is angle R, alternate angles, this angle is also going to be R, right? With these things, now we are going to prove that angle of incidence is equals to angle of reflection, right? So for that, what we are doing? It is from figure. AP is equals to 8. What is that? Distance from here to here is taken as A. BQ. What is that? BQ. This distance is taken as a B. B. PQ is taken as a D. What is that? Distance from here to here is taken as a D. And then PO is taken as an X. Distance from here to here is taken as an X. Therefore, OQ is equals to D minus X. This is going to be D minus X. Right? Then we are calculating AO. What is the AO is going to be square root of A square plus X square. How we got this? If this distance is X, if this distance is A, we know that the triangle APO is a right angle triangle. Therefore, this is going to be the hypotenuse. So this distance is going to be what? Square of this distance plus this distance. So AO is going to be A square plus X square. A square plus square root of a square plus x square. Therefore, we say a is equal to square root of a square plus x square. Similarly, if this distance is d minus x and if this distance is b, this is a right angle triangle and this is going to be what? The hypotenuse. The distance of this is going to be what? Square of this plus square of this. That is by is going to be square root of b square, this square plus d minus x whole bracket square. That is from this figure. So we know what is the value of AO, we know what is the value of BO. This is the value of AO, this is the value of BO. Then, now we are going to calculate the what is known as optical path. What is optical path? We know that optical path is given by basically what is optical path? Optical path is equal to mu into d. Optical path is equal to mu into d. What is mu? The refractive index in which the ray is traveling. So if you multiply the refractive index with the corresponding distance traveled by the ray of light, it gives what? Optical path. Mu into d gives us optical path. Right? Now in this diagram, this is the A medium, this is the class medium. We know that the ray is traveling from A to O and then another reflection from O to B. So AOB is the path covered by the ray of light. AOB is the path covered by the ray of light. Then what will be the corresponding optical path? For the optical path, we have to take the corresponding refractive index. What is that? The refractive index of this medium. That is taken as mu. The refractive index of this medium is taken as mu. Right? So therefore, we say the optical path is given as, the optical path is denoted by the symbol L. So L equals to mu into path AO plus path OB. What is that? Path AO plus path OB into mu. But what is mu? The refractive index of this medium. What is this medium? Air medium. We know that for air medium the refractive index is 1. Right? Therefore, this is going to be 1. We are left with what? That is AO plus OB, because mu equals to 1 for air. But we know what is AO. What is AO? Square root of a square plus x square. What is OB? OB is nothing but square root of b square plus d minus x square. Therefore, this L is going to be, L is equals to square root of a square plus x square plus square root of b square plus d minus x whole bracket square. We call this as equation number 1. So this L is going to be now the optical path. L is the optical path given by equation 1. Right? Now we know that in this diagram the point A and B are fixed. A is fixed, B is fixed. In the sense, this height is fixed A, this height is fixed, it is taken as B. Right? Whereas the incident ray can change its position. Means instead of incidenting at this point over here, it can incident somewhere here and undergo reflection like this. It can incident somewhere here and undergo reflection like this. This one, O can change. O can change from here to here or here to here or here to here. Right? So if you say O is changing, what it means? As O changes, the value of x, as O changes, the value of x changes. Whereas the point A and B are fixed. The point A and B are fixed. Right? But we know that as per the Fermat's principle, whenever a ray of light is traveling from one point to the other point, the path taken by that ray of light is either going to be a minimum, means the time taken for the ray of light to travel from one point to the other point, the time taken for the ray of light is going to be either minimum, or it is going to be maximum, or it is going to be stationary. That is, we know from the Fermat's principle of extremum path, or from the Fermat's principle of the stationary time, the time taken for a ray of light to travel from one point to the other point is going to be either minimum or maximum or stationary. Now what's happening here? So light is traveling from point A to point B. Point A to point B. In between it is undergoing reflection at the point O. Right? So we have to apply the Fermat's principle. We have to apply the Fermat's principle for this light which is traveling from A to B. And we know that the time taken is going to be either minimum or maximum or stationary. So even though the time is minimum, it's a constant. Even if the time is a maximum, again it's some value, some constant. Even if it is stationary, again that value is going to be a constant. But what can change? The x can change. As if the ray falls here, O is going to be here. If the ray falls here, O is going to be here. Means the x can change, right? X can change, right? Therefore, you say, according to Fermat's principle, the length of the path is going to be either minimum, or it is going to be maximum, or it is going to be stationary. Or in other words, dl by dx, rate of change of optical path with respect to x, dl by dx is equals to 0. Why? Because L is a constant. What is L? The optical path. The optical path is a constant. Why it is constant? Because as per Fermat's principle, it is going to be either minimum, which is a constant, some value, either it is going to be a maximum, which is again going to be some value, a constant value, or it is going to be stationary, means a constant value. So if you say L is a constant, when you differentiate a constant, what we get is it's going to be 0. Therefore we say dl by dx is going to be 0 because L is a constant as per the Fermat's principle. That is, it is either minimum, which is a constant value, or a maximum, which is again a constant value, or stationary, which is again a constant value. Right? So dl by dx is equals to 0. Means what? Now we know what is L. So we have to differentiate this equation 1 with respect to x. We have to differentiate equation 1 with respect to x, and that value we have to equate it to 0. So by differentiating equation 1 with respect to x and by equating the value to 0 and by simplifying, we get the final solution. We get the final solution, that is, we are going to prove that the angle of incidence is equal to angle of reflection. Right? So now our job is to differentiate equation 1 with respect to x. So if we differentiate L with respect to x, that is dl by dx is going to do what? Now this is square root of a square plus x square. This can be taken as a square plus x square raised to half. So d by dx of x raised to n. D by dx of x raised to n is what? We know that d by dx of x raised to n is what? Nx raised to n minus 1. Right? So take it as a square plus x square raised to half. Differentiate that. It's going to go on 1 by 2 into a square plus x square raised to 1 by 2 minus 1. What it gives you? It gives you 1 by 2 into a square plus x square raised to minus 1 by 2. That is n x raised to n minus 1. 1 by 2 a square plus x square raised to half. N is what now? Half. 1 by 2 into a square plus x square raised to n minus 1. 1 by 2 minus 1 is going to be minus 1 by 2. Into differentiation is going to be 0. Differentiation of x square is going to be what? It's going to be 2x. It's going to be 2x. Similarly, the differentiation of this term, it is d square plus d minus x square whole bracket raised to half. Again x raised to n. D by dx of x raised to n equals to nx raised to n minus 1. Right? So this is going to be what? 1 by 2 into b square plus d minus x square whole raised to minus 1 by 2 into differentiation of this is going to be 0. Differentiation of this term, that is d minus x whole bracket square. That is like d square plus x square minus 2dx. D square plus x square minus 2dx. So d square differentiation is going to be 0. X square differentiation is going to be 2x. So minus 2x differentiation is going to be minus 2d. So what we are going to get is, so here we are going to get minus of minus 2 of minus d minus x. That is, it's going to be d minus x. It's going to be minus 2d plus minus plus. To simplify this, these 2 and these 2 are going to cancel each other. These 2 and these 2 are going to cancel each other. Correct? So if you simplify this, if you take it to the denominator, what we are going to get is x divided by a square plus x square raised to minus of, or in other words, x divided by square root of a square plus x square. That is x divided by square root of a square plus x square minus, that is minus from this side, plus into minus d minus x divided by square root of b square plus a minus x whole bracket square. This is all equals to what? Equals to 0, because d by d is equals to 0. Right? So we got this. We are further simplifying this. This is going to equal to this side. So what we get? X divided by root of a square plus x square equals to d minus x divided by square root of this term as it is. This term as it is. Now we have here x divided by square root of a square plus x square. What is x? This is x. What is this? Square root of a square plus x square? That is this hypotenuse. So this is going to be a square plus x square. Right? So what is this? This is the angle I. So this is the opposite side. This is the hypotenuse. Opposite side divided by hypotenuse. So what is opposite by hypotenuse? That is going to be sin theta, because sin theta is opposite by hypotenuse. So now in this case the angle is I. So sin I is going to be what? This distance divided by this distance, or in other words x divided by square root of a square plus x square. So from triangle APO, x divided by square root of a square plus x square is going to be what? Sin I. Right? Similarly, if you take a triangle DQO, this is the angle R, alternate angles. If this is the angle, this is the opposite side. What is this? This is the hypotenuse. What is the value of this? This is B, this is d minus x. That is going to be what? This is going to be square root of b square plus d minus x whole bracket square. This is b square plus d minus x whole bracket square. That is going to be bo. Right? So this is the angle, opposite side divided by hypotenuse. This distance divided by this distance. D minus x divided by square root of b square plus d minus x whole bracket square. So this is going to be what? Sin r. Opposite by hypotenuse, sin r. So therefore from this equation we got sin I equals to sin r. Or in other words, we can say I equals to r. What is I? Angle of incidence. What is I here? Angle of incidence. What is r here? Angle of reflection. Angle of reflection. So we come to the conclusion that angle of incidence is equals to angle of reflection. That is exactly the second law of reflection. That is, as per the second law of reflection, we know that the angle of incidence is equals to angle of reflection. So we got I equals to r, angle of incidence is equals to angle of reflection. So this is how we derived, or we proved that the angle of incidence equals to angle of reflection by using what? By using the Fermat's principle. So this is how one can derive the second law of reflection by using the second law of reflection. Right? So what all we did here? We took the case of this. We calculated, we calculated the value of this side AO. We calculated the value of OB. Then we calculated the value of L, the optical path, and we differentiated that with respect to x. we equate it equals to 0, because as per this test, Fermat's principle, it's going to be either minimum or maximum or stationary, which is a constant, right? By equating it to 0 and by simplifying, we finally come to the conclusion that I equals to R. I equals to R. So this is how one can derive the second law of reflection by using the Fermat's principle. I think we'll stop at this point. In the next class, we will derive one more derivation. Till then, you take care. Bye bye.